Welcome to The Explainer. Today, we are digging into a really fascinating security upgrade for the decentralized network, Freenet. We're going to break down how its developers basically taught the network to see in the dark, to spot a super subtle, almost invisible kind of attack.
So, let's just dive right in with the big question. This is the core challenge the Freenet developers were up against. I mean, in a network with no central boss, no single source of truth, how do you know who to trust? Especially when an attacker can sabotage you in a way that's almost impossible to detect.
Okay, to really get the problem here, you first need to understand a little bit about how Freenet works. It's all peer-to-peer. There's no big central server. It's just a web of connections. And your little corner of the network, your node, constantly has to make a choice: which of my neighbors is the best one to ask for this piece of information?
Now, the way it used to make that decision was pretty logical. It looked at two main things. First, how close is a peer to the data I want? And second, what's their track record? What's their overall success rate been over time? And for general performance, that works okay. But it has one critical, and I mean critical, flaw.
And that flaw, well, it creates this massive blind spot. It's an open invitation for a very clever, very specific kind of bad actor. And this is it. This is the ghost they were trying to catch. A malicious peer doesn't have to be a bull in a china shop. It can be a surgeon. It doesn't block everything, it just very precisely targets specific pieces of content, effectively making them vanish from the network. And the whole time, to everyone else, this attacker just looks like a normal, healthy part of the system.
Right, so think about it like this. Imagine you have a postal worker who delivers 99% of their mail perfectly on time, but they lose every single letter going to one specific address. If you're just looking at their overall delivery stats, they look pretty good, maybe a little bit inefficient, but fine. For that one person, though, they're 100% failure. The old system only saw the 99%, not the targeted attack.
And this chart just lays it out so clearly. The attacker's overall success rate looks great, 99%, but for the actual content they're targeting, it's basically zero. That big, broad average completely hides the malicious behavior. The old system was totally blind to this.
So how in the world do you fix this? The solution is a really clever machine learning approach that ditches those easily fooled averages. And it's all based on a pretty simple, intuitive idea.
You see, the big insight here is that context is everything. Instead of asking, hey, how good is this peer in general, the new system asks a much smarter question. It asks, how has this specific peer behaved in the past when dealing with content like this, near this location, and crucially, recently? It's all about looking for specific patterns, not general grades. And this is how it defines similar situations. For every single request, the system logs these four key things. The specific peer, obviously. The contract location. You can just think of that as the address of the content in Freenet's giant distributed storage system, its key space. But the real secret sauce, the coolest part, is that time is a feature. This means the model automatically cares more about recent behavior. So if a peer suddenly goes bad, the system spots it right away.
Okay, so for all you engineers out there, let's pop the hood and see how this thing is actually built. It's not just one big clunky model. It's a series of 3 models that work together in what they call a prediction funnel. And this structure is just, well, it's elegant. First, it asks the most basic question: will this request succeed or fail? Simple yes or no. Only if the model predicts success does it pass it to the next stage and ask, okay, but will it time out? And then only if it's predicted to not time out does it try to predict the actual speed. This is so smart because it solves a classic data problem. You're not wasting time and energy trying to predict the speed of a request that was probably going to fail anyway.
Here's another really clever bit of engineering. They didn't just rip out the old system and drop this new one in. They rolled it out safely. When your node first starts up, it relies 100% on the old, time-tested model. But as it sees more traffic and the new machine learning model gathers data and gets more confident, it starts to blend in its predictions, going up to a 50-50 mix. It's the best of both worlds, stability plus this powerful new detection skill. Okay, so that's the theory. That's how it's designed. The big question is, does it actually work out in the wild? Let's take a look at the results.
So to measure how good the predictions are, they use something called a Breyer score. Now, don't worry about the math. All you really have to know is this. It's a way to grade predictions, and lower is better. 0 is a perfect score, anything under 0.05 is considered excellent, and 0.25 is basically just flipping a coin. And get this, these are the results from a live Freenet peer actually running this new code. Its recent Briar score is just 0.04.
So what does that number actually mean? It means this isn't just some cool idea on a whiteboard. It's working, right now, on the live network. It's making extremely accurate predictions about how peers are going to behave. And that is exactly what you need to spot those sneaky, targeted attacks.
So let's just recap what this upgrade really brings to the table. It lets Freenet catch those slightly worse attackers who were invisible before. It automatically adapts when a peer changes its behavior over time, and maybe most importantly, it knows what it doesn't know. When it doesn't have enough data, it just safely falls back to the old conservative model.
And that kind of leaves us with a final, bigger thought. We've just walked through a huge leap forward for Freenet security for sure, but the idea behind it could be so much bigger. Is this the future? Could we see all decentralized networks having this kind of smart, self-tuning defense system that learns to protect itself, all without a human having to configure a thing?